Okay, this will be the first of the videos that's associated with Chapter 3, where we're going to expand what we learned about alkanes and now look at more specific ways that alkanes align themselves relative, how two carbons, if we're looking at two carbons, how those two carbons are going to align themselves relative to each other. All right, so the first thing we need to consider is the sigma bond between two carbon atoms of an alkane, which you see right there. All right, if you look at it, we're overlapping two sp3 orbitals head on. And what you can see here is that as I turn around that CC bond, I'm not really changing the degree of overlap. So the bond strength doesn't alter by doing a rotation around the carbon-carbon bond. So this, we can look at this as kind of like a propeller on an airplane. All right, so we have relatively free rotation around sigma bonds in general. We'll see that it's not completely free, but it's not because of the change in the degree of bonding. It's other reasons that make it not free. But so there's relatively free rotation around sigma bonds. Okay, we're going to look at the simple molecule ethane shown here. Actually, you see three different structural representations of ethane at this point right now on here. And we're going to consider two extreme arrangements of the hydrogens on one carbon relative to the hydrogens on the other carbon. I'll just call them the left carbon and the right carbon for the projections as drawn here. All right, the one at the top, right here, has the hydrogens on the left totally parallel or overlapping with the hydrogens on the right. And imagine that we bring in a flashlight and shine a light here. What we're going to find here is that the CH bonds on the right carbon are in the shadow of the CH bonds on the left carbon. In astronomy, we call that an eclipse, and in organic chemistry, we also call it an eclipse. This is what we're going to refer to as the eclipsed form of ethane. Every CH bond on one carbon is totally overlapping with the CH bond on the carbon adjacent to it. All right, right below it is the other extreme, and this is where we have the maximum separation between the CH bonds on adjacent carbons. We can't get the CH bonds farther apart than they are in the structure at the bottom of the page. All right, this form of ethane we're going to refer to as the staggered. And again, it has the feature that the CH bonds on adjacent carbon are as far apart from each other as they can possibly be. Okay, these two structures here represent what we call conformational isomers or conformers. They can be interconverted by an allowable bond rotation. Normally, you cannot separate two conformers. The rotation is happening too fast at room temperature. In fact, I think in ethane, you have to get the temperature down to like 2 degrees Kelvin before the rotation completely stops. Okay, so this is really what this chapter is going to be concerned with, conformational analysis of various alkane systems. Okay. All right, so just like to note here that there really are an infinite number of conformations for ethane. Eclipsed and staggered are just the two extremes, okay? Eclipsed as close as the CHs can possibly be, staggered as far apart as the adjacent CHs can possibly get. Okay. In order to represent this, we're going to use a new kind of device here. Clue here is our favorite postal employee up here, Newman. And these are called Newman projections. The alternative way to depict conformers is via the Newman projection. It's not actually named after the Seinfeld character, but after a professor at Ohio State. Okay. All right. So let's look at staggered ethane. And what I'm going to do is I'm going to sort of rotate it, what we call a sawhorse projection here over on the right. Okay, so this one right here, in the upper left, I'm going to rotate it, and we're going to get a new perspective, and this perspective is the one that's going to generate the Newman projection. Okay, so imagine that our eye is looking dead on at this CC bond, so we're looking straight from right there. What you would see is the front carbon right here, which we're going to draw as a letter Y, which has 3 hydrogens on it. I've designated those hydrogens D, E, and F on that one. And immediately behind it is the other carbon, the back carbon, and we're going to represent that as a circle. And that also has those 3 hydrogens on them in the opposite orientation, where we see HA, HB, and HC. Okay, so the Newman projection is a very useful way to represent conformational phenomena. Okay, in a Newman projection, we have a new type of angle called the dihedral angle, and this is the relative orientation of bonds on adjacent carbons. It's the projection angle. Okay, so imagine we just shined a light straight at the compound. This is what we would see. The bond angles don't really work out to be 109 degrees like in a tetrahedron. This is just how they project when they're viewed in a two-dimensional projection. All right, we have a type of angle here called a dihedral angle, which really involves 4 atoms. Most of the angles you've seen before have been bond angles, and those involve 3 atoms. These involve 4. So we're looking at, when we're looking straight at it, like the Newman projection, we're looking at the relative orientation of one of the hydrogens on the back carbon relative to one of the hydrogens on the front carbon. So we're looking at this angle here, HA, to the back carbon, to the front carbon, to HD. Okay, so there's 4 atoms involved in that. All right, and this is 60 degrees. Okay, so when adjacent atoms have a 6 or adjacent CH bonds or adjacent entities or atoms on 2 adjacent carbons have a 60-degree dihedral angle, we are going to use the term gauche to describe that relationship. So that is a gauche relationship, 60-degree dihedral angle. All right. HA is also in a gauche relationship with HF. Okay, also 60 degrees. Okay, the one that's different is HE. HE is totally opposite HA, and if we look at the dihedral angle there, it's 180 degrees. Okay, we refer to that as anti. Anti just means that it's at 180 degree dihedral angle. So in a staggered conformation, everything is either at a 60 or 180 degree dihedral angle. Okay, in an eclipse conformation, everything's either at a 0 degree angle or 120 degree angle. When the dihedral angle is 0 degrees, we just refer to them as being eclipsed. Okay, there's a Newman projection for eclipsed ethane. It's a little bit hard to draw because the back carbon perfectly overlaps with the front carbon, so we have to skew it a little bit, but that's as close as we can get for the eclipse conformation. All right. Now, it turns out that the staggered and eclipse, not only do they represent the extremes as far as the spatial relationships of hydrogens go, they also represent the extremes as far as the energies of these conformations go. Okay, the most stable form of ethane is the staggered form. The eclipsed is 12 kilojoules per mole higher in energy than the staggered. Okay? And this destabilization is known as torsional strain or eclipsing strain. All right. So it's useful to remember this thermodynamic relationship here. Delta G equals minus RT ln KEQ. It's not an equation we'll probably try and solve in this class, but what it means is that the more stable species is favored at equilibrium, okay, so there's more of it. If two things are in equilibrium, the more stable one will be the one that's more abundant, okay, and the more stable it is, the more the higher the relative abundance of the more stable one to the less stable one. Okay, and this also means that as you increase the temperature, the ratio gets closer to 1 to 1. However, at room temperature and well below, ethane is rapidly undergoing this rotation, and if you had a camera with a very fast shutter speed, or if you cooled it down to a point where rotation doesn't occur anymore, you would find that virtually all of the molecules would be in the staggered form. Very few of them would be eclipsed. Okay? All right. All right, so this eclipsing interaction is destabilizing, and I just want to put one more thing out here. If eclipsed is 12 kilojoules per mole higher, this means that it took 12 kilojoules per mole to eclipse 3 pairs of CH bonds. So we're going to divide that number by 3 and come away with the conclusion that it's going to take about 4 kilojoules per mole to eclipse a pair of CH bonds. Okay, now what's the origin of torsional strain? There are two theories. The older one, which I don't think is the one people think is most important anymore, but it's electrostatic repulsion. Bonding electrons are electrons. They're centers of negative charge density, and you don't want to get them too close to each other, and there's a repulsive interaction if they're too close. All right, so that one on the left is what's bad about eclipse, but people started thinking, well, what's good about staggered? Okay, and they noticed that a very favorable molecular orbital interaction occurs here. If you look at the CH bonds that I have drawn in red here, you can see that, well, they're anti 180-degree dihedral angle. But if you look at the sigma bond of the back CH right here, okay, and we're going to look at the antibonding orbital, the sigma antibonding orbital of the back carbon, which we'll call sigma star. You can sort of see that there's a little bit of an overlap, and if you draw this on an MO diagram, what you see is the sigma orbital on one overlapping with the sigma star on the orbital, and there's a slight destabilization here. So only in staggered, where you have this perfect anti-arrangement of hydrogens on adjacent carbons, do you have this favorable molecular orbital interaction. And this is thought to be the reason now for why staggered is more stable. Okay. All right. Let's look at a more complex molecule, butane. You might wonder, we have the Y in the circle that represented the only 2 carbons in ethene that we had. What do we do with 4 carbons? Well, you have to have some other information as you're drawing the Newman projection. Okay, so when you have a more complex system, we have to decide which carbons we're going to cite, which carbons are going to be the Y in the circle of the Newman projection. Okay, so we're going to say if we cite C2, C3, this means that these are going to be the Y in the circle of the of the Newman projection. All right, we could also cite C1, C2, that is down here, but what we're going to see is that it's a little bit less interesting. So we're going to spend all of our time looking at the Newman projections we get by citing C2, C3. All right, in blue here, we're also going to look at the relative energies of each conformation. All right, so the anti-conformation is the most stable conformation of them all, and we're going to assign it a relative energy of 0. Okay, that we're just going to look at the others as how they relate to this one, anti. Okay, what we're going to do is we're going to rotate the back carbon counterclockwise. Okay, clockwise rather, sorry. And when we rotate that 60 degrees, we get to an eclipse conformation. We're going to say this is partially eclipsed. It's 14 kilojoules per mole higher in energy than anti. Recall that eclipsed ethane was 12 kilojoules per mole higher. This is a little bit higher in energy than that, okay, but not a whole lot. All right, we're going to continue this process. We're going to rotate the back carbon another 60 degrees. Okay, and this is going to get us to another staggered conformation, which we're going to call the gauche conformation. And what we see is that the gauche conformation is a little bit higher in energy than the anti, but not a whole lot. It's not nearly as severe as an eclipsed conformation. Okay? All right, we're going to rotate the back carbon another 60 degrees in the clockwise orientation. And here we get to what we call the fully eclipsed conformation, which is much higher in energy than any of the others, 32 kilojoules per mole higher in energy. And this has the methyls really right on top of each other. All right, so there's a couple of types of strain issue going on in this diagram. All right, so we have torsional strain, and this is at a max only in the eclipsed conformations. And they have the word eclipsed as part of the name of them, so you can tell which ones they are. Okay. All right. In addition, we have a phenomenon here known as steric strain. And this is when two things want to occupy the same space. And at the same time, okay? In other words, this is when two things that are relatively large are bumping into each other. All right, the larger entity in this case is the methyl group, which has an electron cloud, okay? So let's go ahead and draw that. So ME doesn't really do justice to what the size of this thing is. All right, those are really the methyl groups. And what we're seeing here is that they're starting to bump into each other. The electron clouds of the carbon and 3 hydrogens that represent a methyl group are starting to bump into each other. And they're bumping into each other quite seriously here. And this is the symbol we use to show that we have a steric interaction or steric strain within our molecule. Okay, they're incredibly close in the fully eclipsed, and this is what's destabilizing the fully eclipsed to such a large extent. All right, so let's just review the strain features that are going on in each of these. We're going to regard the anti, which is shown at the bottom, as pretty much a strain-free molecule. There's no torsional strain since it's staggered, and the methyls are too far away to interact in any sort of way sterically. All right, the gauche is a little bit higher in energy, and this is due to the fact that the methyls are starting to get close to each other. There's no torsional strain here because it's staggered, but there is steric strain present in the ghost conformation. And the steric strain is again from the methyls wanting to occupy the same space. This is known again as steric strain or steric hindrance. All right, in the partially eclipsed, we have torsional strain because it's eclipsed, and the energy is a little higher than in eclipsed ethane because maybe there's a little bit of a steric effect here with hydrogen and methyl, but it's not really all that large because remember ethane was 12 higher for the eclipsed. The partially eclipsed is only 14 higher, so this is not really a serious source of steric strain here. All right, fully eclipsed, methyl is right on top of each other. We can't cram the methyls any closer than they can possibly get in the fully eclipsed interaction, and that's a sterically very destabilizing structural issue that makes the fully eclipsed a very high energy molecule. All right, let's end this here by having you construct your own Newman projection here and draw the most stable form of this compound. Again, you should pause the video and try to do this problem yourself, but I'm going to go right to the answers. All right, draw the most stable conformation for 1,2-dichlorobutane, citing the C1-C2 bond, and assume that a methyl and an ethyl are larger than a chlorine. We're going to find that that's an essential statement required to actually analyze this. Okay, in the IUPAC numbering system, those are the carbons of butane, so we're going to make the Y in the circle are going to be C1 and C2. 0, it looks like an O, but it's a Y and a circle. Okay, let's just call it a circle. All right, so let's look at what we have at C1. Of course, we're going to have C2, but that's going to be the circle that's at the back of the Newman projection. If we look at C1, outside of C2, we're going to have to write an H, an H, and a Cl. Sorry. Okay. If we look at C2, okay, one thing that's attached to it is C1, so we're going to ignore that because that's part of the Y in circle. But we need to think about what are the other three substituents that we're going to put at C2. And what you see here at C2 is that we're going to have a hydrogen, a chlorine, and we're going to have C3 and C4. All right, so CH2, CH3, that's what C3 and C4 is. We've, in the past, referred to that as an ethyl group, so we're going to have, at C2, hydrogen, chlorine, and ethyl. All right, so let's look at the Newman projections that we're going to look at. First, we've been told to draw the most stable one, so we need only consider staggered forms. We know that it could never be eclipsed. Okay, that would be much higher in energy. All right, another question students often have is, where do I start on a problem like this? Well, you have to start somewhere. I know that's it's kind of a flaky answer there, but what you're going to do here is you're going to draw a conformation and then you're going to rotate it 360 degrees, 120 degrees at a time, so you can find the more stable one. It's not necessarily required that you draw the most stable one the very first time you draw it. All right, so I'm going to draw it hypothetically this way for my first orientation. What am I doing? I'm rotating the front carbon 120 degrees counterclockwise. Okay, sorry, can't spell clockwise. All right, so looks like I'm doing this. All right, I get another confirmation here. All right, I'll rotate it another 120 degrees, and chlorine will now go down here. So let's look at the three conformations that we've drawn. Another 120 degrees would be a 360 degree rotation, and that would get us back to where we started. All right, so let's identify the gauche interactions here that are in our staggered conformation. There's one, here's one, but the ethyl is not involved in any sort of gauche interaction, and the only gauche interaction here is with chlorine. Okay, so the left one has two gauche interactions. We're going to deselect that one as not a candidate for being the most stable one, because all the others have fewer gauche interactions, and thus they can be candidates for being the most stable. All right, now here we need to think about an essential statement that was in the problem directions, okay? Methyl and ethyl are larger than chlorine. Okay, that means that the one gauche interaction we have in the compound on the right is with an ethyl group. So that's going to be more severe than the gauche interaction that only involves chlorines, which are smaller. Okay, so we're going to select the middle one here as the most stable one due to having less severe gauche interactions. Okay, I found a typo. I didn't spell interaction correctly. Okay, so let's fix that. All right. Okay, so that's conformational analysis for non-cyclic molecules. Next video is going to talk about cyclic molecules. So this one's going to end right here.